So in order to find solutions to linear congruences, it's extremely useful to have an inverse of our coefficient. So let's talk more about inverses. So I said that, or I suggested that they don't always exist. Here is a nice criterion. Oh my gosh. Theorem. Okay. An inverse of A mod M exists if and only if the greatest common divisor of A and M is 1. So if and only if A and M are relatively prime. And let's go ahead and prove this. So what does an inverse mean? Let's start from there. So inverse means B such that, well, let me say means there exists a B such that AB is congruent to 1 mod M. And then let's unwind what this congruence means. What does this mean? So we have a couple ways of describing it, but here is one. This whole statement, or rather, this whole statement, is equivalent to saying there exists B and some integer t such that AB is equal to 1 plus t times m. That's one way of unwinding this congruence, right? It just means that AB is equal to 1 plus some multiple of m. And what does this tell us? Well, we can rewrite this equation as 1 equals, let me say, negative b times a plus t times m, something like this. And saying that there are integers, b and t, that make this equation true, you may remember from Bezout's theorem and our rules of divisibility that this, again, is equivalent to the fact that the GCD of A and M is equal to 1. So let me unwind this step a little bit more. Just to say it again, in a little more detail, exists B and T such that minus B, but okay, this isn't changing much, minus B times A plus T times M equals 1, if and only if GCD of A and M is 1. Okay, so this is the last step. And let's look at each direction. So this direction is just given by divisibility rules. So the GCD of A and B divides A and it divides B. So looking at this equation, oh, I'm sorry, I'm saying A and M. Okay, it divides A and it divides M. So by our divisibility rules, it divides this whole thing. And if your GCD divides 1, it must be 1. It can't be smaller. So that's that direction. What is this direction? This direction, remember, is exactly Béziers' theorem. Béziers' theorem says if your greatest common divisor is 1, or if your greatest common divisor is whatever, then you can find a linear combination of those two things that equals the greatest common divisor. So it's exactly this backwards direction. So that completes the proof. It's essentially just saying that having GCD equal to 1 is equivalent to having something you can multiply to get 1. So we have this nice simple criterion for when such an inverse exists. And the proof also tells us how do we find an inverse? Well, let's look a little bit carefully at this proof. If we look at, so B is our inverse, essentially, and oh my gosh, I think I got my signs wrong this whole time. It should be positive B and negative T. Is that right? Yeah. Oh, someone told me in the chat that the signs were wrong. Yeah, I think you're right. So this is B minus T. How convenient. Okay, how about that? Much better. So let's get back to where we were. How do we find an inverse of A mod M? So our inverse in this proof we were calling B. And this last sort of step is telling us that B, we can find it by computing Béziers coefficients for A and M, right? That's something that we did yesterday, I believe. If you know that the GCD is 1, you can find that using the Euclidean algorithm. And then working backwards from the Euclidean algorithm, you can find coefficients, Béziers coefficients, that realize that GCD. And what this is telling us is that the inverse is exactly a Béziers coefficient. So we can find an inverse of A mod M by using the Euclidean algorithm to find Béziers coefficients. So let's see an example of this. Find an inverse of 23 mod 29. And I mean, this is very nice because as soon as your numbers start getting any kind of big, it's going to be horrible to just figure out what the inverse is on your own. So here is a nice, easy algorithm for writing it down. So, hey, let's even review the Euclidean algorithm. How does it work? So 29, it's just the division theorem again and again. So 29 is 23 plus 6, I believe. And then 23 is 6 times 3 plus 5. And then 6 is 5 plus 1. So when we get a remainder of 1, we're finished. And that's the GCD. And it's also at this point that we can work backwards. So if we turn this equation around, it tells us that 1 is equal to 6 minus 5. And then if we substitute this equation in, 1 equals 6 minus 22 minus 6 times 3. And let's rearrange that a little bit. Negative 22 plus 4 times 6, I believe. Something has gone wrong. I've written 22 when I meant 23. Is that what happened? That is. Okay. Ah, thank you. And then rewriting this one to replace the 6, we get 1 equals negative 23 plus 4 times 29 minus 23. And that is equal to 4 times 29 minus 5 times 23. So let's look at what we were looking for. Find an inverse, right? So we found our basic coefficients. And we want to find an inverse of 23 mod 29. So if we look at this equation, this is telling us that 23 times negative 5 is congruent to 1 mod 29. So negative 5 is an inverse of 23 mod 29. Or, again, we have many inverses because we can get more by adding or subtracting 29. So, for example, we could also say 24 is the unique one in 0 to 28. So this is how we find inverses, mod m.